Here we have a very important page of notes. It's really the page of notes that gives us meaning to the equation that we just derived, that charge as a function of time as the capacitor charges up. It allows us to understand a graphical interpretation and a physical interpretation of the charging of the capacitor in general. Really important page of notes. My advice to you is for this unit, for what we are doing, you should memorize the equation that the charge on the capacitor builds as a function of time based on Qmax times this bracketed term 1 minus e to the minus t divided by RC. Suck it up and just memorize this equation. Once we do that, we're in business to now pull our understanding out of this equation, because we can recall, hopefully, that the bracketed term is this decimal percent to Qmax, so it is going to go between 0 and 1. It could be 0.25, 0.5, 0.75, and so on. The other thing that allows us now to do is give meaning to this R times C that we have left together here. We take a look at this equation. We can see that little q has units of coulombs, capital Q has units of coulombs. That means the bracketed term needs to be unitless. It is just as we have shown here, the decimal percent to Qmax, 0.25, 0.5, but no units. So that means R times C has to have units of seconds, so that I have seconds on the top and seconds on the bottom canceling out. So the units, ohms times farads, have to be seconds. So it's interesting, and we're going to talk more about that a little bit later in the course. But from right now, let's just take a look at a specific example of an R and a C equaling some number of seconds. So if I have 2 ohms and 1 farad, as it shows here, that means I have an R times C, which is also called a time constant. We'll talk more about that in a second, of 2 seconds. We want to give life to the 2 seconds in terms of the charging of the circuit. What's going on at time t equals 2 seconds when this circuit is charging? Well, when R times C equals 2 seconds, right, and little t equals 2 seconds, so at time 2 seconds, which corresponds to the RC of 2 seconds, we are at 63% full, roughly 2/3. So there's no magical meaning to it, other than it happens to equal to roughly 2/3. So it gives us a way of comparing RC circuits. So when little t, so what I have plotted on the x-axis here, so I got to keep my time constant t and my time t a little bit separated. So what I have plotted on the x-axis is little t. So that's the t on the top. So when the t on the top equals 2 seconds, so when little t equals 2 seconds, we are roughly 2/3 charged. By far, this that we've just talked about is the most important thing for you to really grasp and understand the functioning of the RC circuit as it charges. The reason this is so important is because it then will, everything we're going to do on the bottom part of this page flows from this analysis. Now, the last thing I want to do on this top analysis is just to indicate when little t is equal to roughly 4 times RC. So fully charged in about 4 time constants means little t equals a seconds value of 4 times RC. When I plug in little t equals 4 times RC, I get 1 minus e to the minus 4, and that's going to be roughly 98% charged. We could keep waiting. We'd get to 99 after 5 time constants and so on. But 4 time constants is a good ballpark number to say we're up here at the 98th percentile in terms of being fully charged after about 4 time constants. In this case, 4 time constants would be about 8 seconds. So somewhere out here for time constants would be about 8 seconds. Okay, the reason everything else flows is that we're going to be using this Q equation for everything else we do. Q equals CV, so the voltage across the capacitor is the charge on the capacitor divided by C. So notice that the voltage across the capacitor and the charge across the capacitor have the same profile, as we would expect, I hope, that these two profiles aren't identical because the charge and the voltage go together. And the last thing we can see that flows from our Q as a function of T equation is if we want the voltage across the resistor that's in line with the capacitor as it's charging, then we need V equals IR for that resistor, I equals dQ dt, and there you have it. We are going to take the derivative of that Q equation that we memorized, Q max times the quantity 1 minus e to the minus t on RC. We take the derivative, and look what we get. We get the current is given by Q max on RC, V equals IR, so we plug that in for the I, and the R's cancel out. So we get the Q on C max, so e to the minus t on RC. So it falls off exponentially in terms of the voltage across the resistor. The current across the resistor, notice, also falls off exponentially according to e to the minus t on RC. So a lot going on this page. I'm definitely going to talk more with you about this page of notes in class, and we'll talk about these functions and hopefully get everything to kind of sink in and be able to answer questions when we are together. But I think the bones of it is here. Make sure you get everything down into your notes. If there's annotations you want to make based on my comments from the videos, get those in and we can talk about it more in class.